Hey everyone, my name is Paul-Marc DiFrancesco and I'm a master's student at Queen's University. Today I'm going to be discussing assessing rock slope hazards from digital rockfall databases and some of the best practices and lessons that we've learned in conducting this research.
Rockfall inventories, or rockfall databases, are compilations of known rockfall events over a specified area and length of time. They allow us to analyze spatial temporal distributions, quantify rockfall hazard, and learn why they occur and when we should anticipate them to occur. There are numerous challenges in actively monitoring rockfall activity so that we can populate their occurrence into a rockfall database. The first being that we're limited to what we can see from the infrastructure level. Here on the bottom we see two different vantages of the White Canyon, where it may be difficult to see rockfall sourcing areas which may pose threat to the track. Another challenge is that it's difficult to see evidence of rockfall unless rockfall fragments are of a significant size or if the rockfall impact the infrastructure. On the right hand side here we can see the ditches along the White Canyon, and it may be difficult to pick out which new fragments are a result of newer rockfalls which have previously occurred. And lastly, we're interested in rockfall activity across a large span of corridor. So it may be hard to do all of this work along large stretches and to be actively accumulating all of this information together. This is where remote sensing becomes a very useful and powerful tool for monitoring hazards, because with remote sensing we can capture point clouds which allow us to digitally monitor rock slope activity. These point clouds provide a permanent digital record of the terrain at a particular instant in time, and here we asterisk permanent because we should always have good database practices so that our data sets are actually permanent. By comparing these data sets over time, we can accurately identify where change is occurring on the slope. From this, we can begin to develop rockfall inventories, and we can learn and understand the rock slope processes as we continue to monitor them. Here we see at one of our sites, Nalaka Hill, with several of the extracted rockfall volumes that are spinning in 3D. The rest of the rockfall data is projected onto a photogrammetry model and colorized by their volumes shown in the top right-hand corner. Seeing how powerful these datasets are, there is a need to develop software tools which can automatically analyze our data and inform us of key information pertaining to geohazards. These software tools should allow for practitioners to spend less time doing manual processing of datasets so that more time can be spent making important engineering decisions while being informed about these geohazards. From this requirement, we can agree that these software methods should be free of systematic error contributing to bias, such as including false rockfalls in our database. These software methods should be accurate, computationally efficient, and optimally automated so that the computer does most mundane tasks and all engineering decisions are left to the experts. With the future development of remote sensing technologies, the requirement for such tools becomes much more needed because data may be more vast and more frequent. Mobile laser scanning systems can capture near vertical terrain across large lengths of corridor. Improved computing hardware, software, and cloud computing architecture can support the massive processing of this data. Here we see various Regal laser measurement systems mounted on a UAV, helicopter, and a train. The usage of these mobile laser scanning systems has been demonstrated in England, where they monitored over 20 kilometers of coastal cliffs. Developments in automated systems for frequent data capture has also been presented by Ryan Cromer and Nick Rosser's group, where the frequency of data capture can greatly improve our understanding of rockfall processes and can help us track deformation and see progressive failure of the rock mass. And now, so we're going to outline how you go from this point cloud data into rockfall data. Here's the process from going from point clouds into individual rockfalls to be populated into a database. So first we conduct change detection between two sequential datasets. This allows us to extract the fronts and the backs of changing objects. We then take this change detection signature and remove all noise and artifacts. We then cluster nearby points together to create individual rockfall objects. These objects then must be classified to ensure that they are rockfalls. We can then put these individual rockfall objects into a processing pipeline to compute their volume, their spatial parameters, such as shape or proximity to other rockfalls, and can put that all into our database. So now we're going to show you what some of this data looks like by doing a fly-through of the western portion of the White Canyon. This is one of the longest monitored sites in the world, as well as one of the largest sites monitored by terrestrial laser scanning. Here we're visualizing all of the erosion data occurring from April of 2013 to March of 2020. This data includes debris which has been removed from the ditches, as well as debris moving throughout the channels, and rockfall occurring on the cliff faces. Each changing object has been segmented and colorized to different colors so that we can tell them apart from another when they superimpose each other, such as some of these debris movements occurring in the channel here. And as we progress along the slope, we see that there are a few areas of cliff face which have not had any rockfall activity. And again here we see some of the ditching efforts along the trackside. And not only can we see what's occurring adjacent to the track, but we can also see everything which is in line of sight from our terrestrial laser scanner. Up into the very far portions of the slope, the very high reaches, we can still see rockfalls occurring along these cliff faces. These rockfall fragments accumulate into the upper portions of the channel and propagate downwards as small debris movements. We have also recorded very large debris flow movements, which have fully cleared the channels. And here again, we can see the superimposition of all of these small events occurring. These rock sheds are 20 meters long each for scale. And just adjacent to them, we have this 2,600 cubic meter event, which was detected in June of 2013. And surrounding it, we see some of these precursor events, which occurred prior to the rockfall. And on the interior, we see some of the rockfalls that occurred after this rock mass had failed. And now we get to a very active portion of the slope adjacent to the track level, which has almost seen a new fresh surface since we began to monitor it in April of 2013. And so looking at this fly-through, we can really see how valuable this information is, as it allows us to culminate all this rockfall information into one place. And we can start to peel this information together and use it to make engineering decisions. And again, here we zoom out and we show you the massive scale of this site. And that wraps up this fly-through of the western portion of the White Canyon. So now that we've covered how to extract rockfall from our datasets and what the datasets look like, we're going to look at some of the best practices for semi-automated rockfall extraction. And we're going to look at some of the work that we've done and analyzing the potential errors within this workflow. We conducted 2 studies on improving first change detection and secondly volume estimation in 3D. First, we'll be discussing improvements done on change detection. As discussed earlier, change detection involves identifying changing areas on the slope and is therefore a critical process in our workflow. Here, we evaluated a commonly used algorithm, which is the multi-scale model-to-model cloud comparison, and we tested its spatial averaging component, which corresponds to the diameter of the searching cylinder shown below. We tested this on a great database that we created for CN Ashcroft Mile 109.4, which has seen a lot of rockfall activity over the years. Here we can see the centroids of each rockfall event colorized by when they occurred and sized by how large they were. Here we focus on the 3D data adjacent to the tunnel portal shown on the left-hand side. On the right-hand side, we see the 3D rockfall data, which here is colorized by volume, where cool colors are small volumes and warm colors are larger volumes. On the bottom left corner of each inset image, we see the projection diameter that was used, which is the spatial averaging component of the change detection algorithm. Comparing the 20 centimeter and the 100 centimeter projection diameter, we can see that as we do more spatial averaging, we start to lose some of the small rockfalls that we extract, and the boundaries of the rockfalls that we extract become blurred. When we culminate all this data together in a magnitude cumulative frequency plot, we can see that more spatial averaging results us in losing a lot of rockfalls that were extracted in the range of 0.001 meters cubed to 0.1 meters cubed, as we can see here. We therefore determined that less spatial averaging captures more rockfall in the extraction at the cost of us needing to remove more leftover noise that's present in the change detection signature. One might argue that these small rockfall magnitude ranges don't matter in the grand scheme of rockfall hazard along transportation corridors. However, we have documented several cases where very small magnitude rockfall events actually tell a larger story in a future large failure of rock mass, such as in the right-hand side, we see again this case of the 2600 cubic meter rockfall event and numerous of these precursor events which occurred in proximity to it before the final failure of the rock mass. We also see this on the left-hand side. However, using our example of spatial averaging, we can see that these small rockfalls outlining the boundary of the eventual failure are not captured with more spatial averaging. We now move onwards to some of the contributions we've made in improving volume estimation in 3D for the rockfall extraction process. A point cloud, as we can see on the right-hand side of this image, is not a fully enclosed entity, as opposed to this surface mesh, which is. To compute the volumes of point clouds, we therefore need to reconstruct a digital representation of the object as a surface. In doing so accurately, giving our challenging input data is difficult. And so we have been evaluating various surface reconstruction methods best suitable for this task. Here are some of the different algorithms that we've tested. Some overestimate the volume, such as the convex hull. Some are able to accurately model the surface, however, create holes in the interior of the object, resulting in an inaccurate volume estimation. And then others do a fairly good job at being robust enough to completely fill the object while capturing some of its surface details, such as the power crust in the iterative alpha shape. So if we plot again all this information onto a magnitude cumulative frequency chart, we can see the potential volumetric error associated with using different surface reconstruction techniques to estimate volume. Interestingly, the slope of each of the magnitude frequency relations are similar. However, as we pointed earlier, the default alpha shape underestimates the volume, whereas the convex hull overestimates the volume, and the power crust and the iterative alpha shape lie somewhere in the middle and validate each other. The key takeaways of this presentation is that remote sensing data provides us with detailed information from which we can extract important information concerning geohazards. We need to develop and validate the methods used to automatically extract this important information so that we can give database results with minimal errors, optimize our time to be allocated on interpreting data rather than manually processing it, and to prepare us for the abundant and large data sets captured by newer systems. Some of our future work in this project includes learning how localized detailed monitoring information can complement regional hazard assessments. We also want to add additional information into the Rockfall databases. This includes localized precursor activity, deformation profiles, and the proximity to discontinuities in the rock mass. Understanding all these factors can help us have a better understanding of why rockfalls are occurring and might be able to improve our methods on forecasting high hazard areas of rockfall. Additional work includes smart systems capable of detecting noise and systematic errors produced by the change detection algorithms, since as we showed, we want to have the least amount of spatial averaging as possible. And then lastly, smart systems capable of classifying the mass movements that we capture is also needed, such as is this a rockfall or is this a talus movement? And Yanni has been doing some really great work in doing some of this. Here's a list of some of the references that were dispersed throughout the presentation. We'd like to acknowledge our project funders, NSERC, CN, and CP Rail, as well as our project collaboration with University of Alberta, the Canadian Geological Survey, and Transport Canada. Thanks very much for your attention, and I'd be very happy to answer any questions.